And so what we can end up doing with this equation is turning it into a little formula. Again, at least at room temperature, and if they don't mention it's at room temperature, we just assume it is. We've got one of our important formulas on this notes page right up here. 1 times 10 to the negative 14th will always equal the H3O plus times the OH minus. So if you know one, you can solve for the other. If you know one of the concentrations, you can solve for the other. So let's first look at this handout here, and let's find the values of H plus and OH minus in a neutral solution at 25 degrees Celsius. This might be the next slide here. So this is something I did on the board yesterday. This is where we know if it's a neutral solution, you have equal amounts of H3O plus and OH minus. So let's go ahead and list that here. Again, H plus and H3O plus are synonyms. This is just the shorthand way to write H3O plus, because that proton really doesn't exist on its own. It finds a water molecule. If the solution is neutral, then these two numbers are equal to each other. And we don't know what they are, so let's just call those X. Maybe you remember what they are from yesterday, but we're going to start off like we don't know what they are. So then we can say 1 times 10 to the negative 14th equals H3O plus, which is the same as H plus, times OH minus 1 times 10 to the negative 14th equals X times X. So this is kind of like what we did with some KSP values the other day when we were trying to find the concentration of those. X squared equals 1 times 10 to the negative 14th. Now I'll just solve this for X. Take the square root of both sides. And I'm going to end up getting that X equals 1 times 10 to the negative 7th. So what that means, if the solution is neutral, then the concentration of H3O plus is 1 times 10 to the negative 7th molar. So the unit for this is molarity also. I should put that on the screen there. And the concentration of OH minus. Is the same. And when I see scientific notation, sometimes I don't really think about what it actually means. So I like to take it out. 1, 2, 3, 4, 5, 6, 7. And then also this. 1, 2, 3, 4, 5, 6. So if you took some perfectly pure water that's just been sitting out at room temperature, then the concentration of each of these would still be this really teeny tiny number. If you add a little acid to it then, if you have this beaker of water, you add a little acid to it, that's going to change these numbers, but their product is still going to be 10 to the negative 14th. So now we're going to find out you can change one and it changes the other, but if one goes up, the other goes down, because at room temperature they still have to get to the same equilibrium constant value in terms of their product. So that's what we can do on the next 2 bullet points on your handout. Let's see what it looks like when it's not exactly just neutral solution, it's one or the other. So on this next bullet point it says, if H plus, or same thing as H3O plus, is 4 times 10 to the negative 9th, what's the hydroxide concentration? Is it acidic or basic? All right, well, let's give that a try. So once again, every time we can just say 1 times 10 to the negative 14th equals H3O plus times OH minus. Now this time they're not going to be equal to each other, so we're not just going to set it up to be X squared, otherwise we get the same answer. This time we know this one, so we'll put that in place of H3O plus. And then we're going to solve it now for OH minus. You can call it X if you want to, or you can just call it OH minus. we'll divide both sides by that. And I'll be sure to use parentheses around this denominator when I work it on my calculator. Just to make sure my calculator knows that the 10 to the negative 9 goes downstairs. Hit the wrong button here. 1 times 10 to the negative 14th. Can't seem to hit the right buttons today. There we go. All right, so here we go. I'm getting 0.0000025. I'll put it in scientific notation. You don't have to put it in scientific notation, but it's going to be easier to compare them if you do. I'm getting 2.5 times 10 to the negative 6th. So then if I need to decide if it's acidic or basic, what I want to do is ask myself, which one is greater? The H plus concentration is 4 times 10 to the negative 9th, and I just found that the hydroxide concentration is 2.5 times 10 to the negative 6th. All right, which one's in greater concentration? Hydroxide or H plus? Yeah, hydroxide wins because 10 to the negative 6th is actually bigger than 10 to the negative 9th. So if you have more hydroxide than you have H plus or H3O plus, same thing, then that means it's going to be a basic solution. And there's another way to find that answer too. You could also use the pH formula that we looked at earlier with that H plus concentration, and you're going to get somewhere around 9, maybe not quite 9, but I can estimate that the pH is 9, about 9. Why would I estimate that the pH is about 9? Yeah, good. Move the bell ringer from yesterday. We can focus on the exponent. So for your H plus concentration, if that exponent is a 9, you know the pH is going to be about 9. It might actually be 8 point something, but it's going to be around 9 because of the exponent on your scientific notation. That's what these logarithms are all about. Okay, let's try the next one here. It goes the other way. If the OH minus is 7 times 10 to the negative 13th, what's the H plus? Well, once again, we can say 1 times 10 to the negative 14th equals, this time we're looking for H plus, times OH minus, which is 7 times 10 to the negative 13th, okay, I'm getting H plus concentration is about 1.4. I guess with sig figs I could just round it to 1 because that says 7 there. It's about 1 times 10 to the negative 2. Right, so one thing I know is that H plus is greater in concentration than OH minus. That means it's got to be acidic or basic. Acidic, acid wins. And then I can also know pretty close to my pH value. If I wanted to estimate the pH, again, take your H3O plus concentration and look at that in scientific notation. The pH is about 2. I could find it more specifically if I used all the numbers, all the digits in my calculator here. But the pH is about 2, so that reminds me that it's got a acidic pH. So that's one relationship that we're looking at. If you know one, you can find the other because you can set their product equal to Kw, which at least at room temperature is 1 times 10 to the negative 14. One thing that's kind of cool, does anybody know human body temperature on the Celsius scale? 37, yeah. Good job. 37. At 37 degrees Celsius, Kw is not 10 to the negative 14. So in your body, 7 is not necessarily neutral. It's got a different scale. It's almost a 0 to 13 scale. So about 6.5 is neutral in the human body because temperature changes Kw. And so if you set x squared equal to anything other than that, it's not going to be exactly 10 to the negative 7. It would be something else. So you'll actually get a different neutral pH at human body temperature. Not hugely different, but it's off by just a little bit because it's about a 0 to 13 scale instead of a 0 to 14 scale. All right, well this is a review for us at this point because we saw the bell ringer and we've used this a little bit. So most important equation here is the pH equation, that pH is negative log of H3O plus. And that one is on your sheet right here. Up above that one, I don't know if I have this typed in the notes or not, so I'm going to go ahead and put something else on the screen here. Up above this equation, I want to talk about a question Maddie asked. What if you wanted to solve this for H3O plus? Well, logarithms are all about 10 to the power of something. So the rearrangement of this equation that we can just put on our little handout right above that central formula right there is if you want to know the concentration of H3O plus or H plus, it's the same thing, you do 10 to the power of the negative pH. That's kind of the reverse of a logarithm, is taking 10 to the power of something there. So this is another important equation that we'll use quite a bit. H3O plus is 10 to the power of negative whatever the pH is. That way you can go forwards or backwards, whether you're solving pH or using a pH to get the H3O plus. And so this is, again, you don't need to write this down. I don't think this is what we were talking about yesterday. Where did that scale come from? The 0 to 7 is acidic, greater than 7 is basic. Because in pure water, we just found that H3O plus is 10 to the negative 7. If you take the negative log of 10 to the negative 7, you're going to get 7. So when these two are equal, the pH is going to be 7. Also, when the pH changes by 1, so if the pH goes from 7 to 8, that means that the solution has 10 times as much hydroxide than it did before. If it goes from 8 to 9, then it has 10 times more hydroxide than it had before, because hydroxide is on the basic side. If you start at 7, you go from 7 to 6, that means the solution became 10 times more acidic. If you go from 6 to 5, it became 10 times more acidic again. So if you go from 7 all the way down to 5, it became 100 times more acidic. So every time you change the pH, it means the acidity changed by, in terms of the H3O plus concentration, it changed by a factor of 10 because it's a logarithmic scale. And this little sheet is on this little chart's on your sheet that I gave you, and you can kind of see that factor of 10 relationship here. The H plus in molarity, if you have a 1 molar solution of a strong acid, it would give you a 1 molar solution of H3O plus. So Essie, you would not probably want to drink that if it were 1 molar concentration of strong acid. That would be where it would start really irritating you as you drank it. Irritating your throat, probably destroy your teeth. Not good for you. But if it's a 1 molar concentration of a strong acid, it has a pH of 0. We don't think about a pH of 0 very often, but yeah, 1 molar is a pH of 0 there. All right, if you have a 0.1 molar solution, so now it's 10 times less concentrated in acid, it's now a pH of 1. If that is diluted by a factor of 10 and it's 0.01, now it's a pH of 2. So every time the acidity drops by a factor of 10, the pH is rising by 1. And you can think about going the other way too. I think it makes more sense to start neutral and then lower the pH it's becoming 10 times greater concentration of the H3O plus. Because it's a logarithmic scale, it's based on 10 to the power of all those numbers there. And you could keep going and going all the way to a pH of 14, but there's only so much room on the chart, and these numbers can get really, really teeny tiny as you went that way. But on the other side of it, the hydroxide is going the other way. The hydroxide is increasing in concentration by a factor of 10 every time you increase the pH. So if the hydroxide goes up, the H3O plus goes down. There's our chart we were looking at yesterday with all those pHs on it, pHs of different substances. So you can see because it's logarithmic, there's a huge variety of concentrations of H3O plus possible. All right, so now let's, again, practice with the pH equation. We've done that a little bit. I also want us to practice estimating it. So using the pH equation, we could find the specific pH if the solution is 2.4 times 10 to the negative 13th molar in H3O plus. So we'll just do negative log of that number. But let's also practice estimating it. But I said I don't have a calculator, and I just want to estimate about what is the pH if the H3O plus concentration is 2 times 10 to the negative 13. It's about 13, good. Let's find out specifically what it is. We know it's going to be close to 13. All right, you already did it for me. Thank you. 12.61. Thank you. Whoops, let me go back. So we say pH is negative log of 2.4 times 10 to the negative 13th. I know it's going to be around 13 because of that. And you found it is 12.6. So if it were exactly 1 times 10 to the negative 13th, it would be right on 13. But that 2.4 messes it up a little bit. So it means it's a little bit more acidic than if it were 1 times 10 to the negative 13th. So the pH is a little bit lower than 13. Is the solution acidic or basic? Basic, because the pH is greater than 7. Let's go the other way. This is the first time we'll use that other version. So let's say you had some apple juice and you put the little strip in it and you had really, really good color vision. So you weren't just saying it's about 3 or it's about 4. You were like, oh, it's just between the two colors of orange and yellow orange or something, and it's red orange and orange probably, and it's 3.76. Here's how you find the H plus concentration. H plus or H3O plus concentration is 10 to the negative pH. That's the opposite of a logarithm, log base 10. 10 to the negative 3.76. And that's not a good enough answer, just saying 10 to the negative 3.76. I want a specific answer there. So let's all try that in your calculator. I'll just do 10, and then I'll find that little caret button. I'm sure you know how to do that. 10, little caret button, negative 3.76. The little arrow hat thing. And I need some help here. So Carter, what'd you get for this for the H3O plus concentration here? Good job. Did somebody say they got 5,000? Because that we need to look at your calculator. You got it. Okay. Oh yeah, I'm glad you noticed that. So everybody, be sure you put that negative in there. What's the unit supposed to be for this? Good, molar, because it's those brackets. They mean we're finding the molar concentration or the molarity. So if you can go one way, you can go with the other. The next thing I want to talk about, so far, we've always been focusing on H3O+. It's the favorite child. It gets all the attention. But you know what? OH- has also been changing this whole time. So we can also think about all this acid-base stuff. We lived in an alternate universe, and they said they're going to focus on hydroxide. Then you could have a 0 to 14 scale based on the concentration of hydroxide. And there's one, it's called POH. So the POH scale is like the reverse of the pH scale. They always will, they're like pairs that will always add up to 14. So that's the other thing we see on the top of this sheet, this notes page, something about POH. So in chemistry, a lowercase p always means negative log of something. So we've got pH Now we're going to look at POH. When you do the buffers lab tomorrow, you'll do pKa. Lowercase p means negative log of something. Well, look at this. pH plus POH for a solution always adds up to 14. So if you, for whatever reason, wanted to focus on the hydroxide concentration, maybe you knew the hydroxide concentration, and you wanted to do that to get a pH, there are multiple ways to get to that answer. So here we go again. The lowercase p means negative log. So that's what that means. It means you're going to hit negative log. These are some of the examples we're going to see. POH, there's one called pKw that we don't use very much as far as calculating it, but pKw equals 14 at 25 degrees Celsius at room temperature. pKw is 14 because it's just the negative log of 10 to the negative 14th. So we saw already that if you multiply the H3O plus concentration times OH minus concentration, you'll get 10 to the negative 14th. One of the things you can do in math and learn about logarithms and is everything, if you multiply two numbers and you separate them out as their logarithms, you could add up their logarithms. That's where we get this equation. The most important thing is the stuff in red here, which you can actually use. If you know the pH of a solution and you want to find the POH, well, they would add up to get 14. So you can subtract 14 minus the pH or the POH to get the other one. So pH plus POH of a solution, at least at room temperature, it's going to add up to 14. If you were in human body temperature, it might add up to like 13.5 or something like that because the pH scale is shorter at higher temperatures. All right, so here's the question that's on your sheet. In a solution, the hydroxide concentration is 5.62 times 10 to the negative 11th molar. What is the pH? So one way to do this would be what we've been practicing, which would be to do 10 to the negative 14th equals H3O plus times OH minus. Find the H3O plus and do the negative log of that. There's another way to do it with the pH scale and the POH scale. I think it's easier. So let's try this other method to get a pH. You could first get the POH. So POH is going to be the negative log of the hydroxide concentration. So if you have a base, you might want to focus on hydroxide first, as if you lived in that upside down world where they decided to focus on hydroxide. Because if you know one, you can always find the other. If you know a hydroxide, there's a way to find H3O plus. One way is to realize that their product has to be 10 to the negative 14th. The other way, it's kind of more roundabout, but I still feel like it's easier. You could find the POH first. So you find the POH of that for me. We're going to do negative log of the hydroxide concentration. If anybody's getting different numbers than what we get when you type this in, let me know because I can make sure you're finding the right log button on your calculator and all that. I know it's got to be around 11. MK, what did you get for the POH? Good, 10.3. Then I can do this to change it into a pH. pH plus POH equals 14. And again, this is 14 is an exact number, all right? So we don't have to worry about that in terms of our sig figs. So if I'm looking for the pH, I can just do 14 minus the POH. They have to add up to 14. 14 minus 10.3. Is it 3.7? Is this solution acidic or is this solution basic? Pavitra? Acidic. So when the pH is less than 7, it's acidic. When the POH POH was 10.3, so if POH is greater than 7, it's acidic, because the POH scale is backwards compared to the pH scale. So if you know pH, you can find POH. If you know POH, you can find pH. If you're dealing with the base in the first place, you might find the POH first and just subtract from 14. All right, so just some quick and easy practice now with the pH and POH scale. When the pH is 7, at least at room temperature, Vivi, what's the POH? They have to add up to 14. Make it easy. 7, yeah. So they have to add up to 14. So if pH is 7, POH is 7. Now we'll see, they're not the same all the time though. Oh, and also with this first one, that would be a neutral solution. Let's just make a note of that, neutral solution there. When the pH is 3, what's the POH? Alice? It's 11. It's that easy. Just subtract from 14. Is this solution acidic or basic, Kira? Yeah. The second one? Focus on your pH here. Acidic. Yeah. Yeah, acidic. So focus on your pH based on those rules to decide if it's acidic or basic, because we know it's the less than 7 for pH is acidic. The POH is kind of hard to think about because it's a reverse scale. Broadfoot. What's the POH for the third bullet point? 8.6. Thank you. Good job. 8.6. This is tough for me on a Thursday morning. Ainsley, is the third bullet point acidic or basic? Acidic. It's acidic again. Good. pH is less than 7. And this other one goes kind of in the reverse order for the question, but it's just as easy to get the answer. When POH is 4.2, what's the pH? Essie? 9.8. Good, 9.8. Is this solution acidic or basic, Davis? Basic. Basic, good, because the pH is 9.8. That's more than 7. All right, so those are the relationships between pH, POH, H3O plus, and OH minus. One other thing you can do with the POH, there's a little room on the bottom of, there's a little bit of room maybe on the margin or somewhere. I just realized one other thing that would be useful to have. We've said that the erase all this. Relationship with POH is negative log of the OH minus concentration. What if I wanted to solve that for OH minus? Just like I did with the pH equation earlier. If I wanted to rearrange that and solve for OH minus, any ideas what I would put on the other side of that? What's the opposite of a logarithm, log base 10? Pavitra? Great job, yeah. 10 to the negative POH. So that could be helpful. There's other ways to get that, roundabout ways to get it too, based on the pH scale and everything. But that might be a helpful way to fill out a chart like this one on the back of the sheet that we're about to practice using all these equations on. All right, so it says complete the following table by calculating the missing entries. So this would be like a chart. We're trying to put in a lot of information. Let me go back here. Hit the wrong button. We got to fill in all the missing boxes on this table. The first two columns are going to be super easy. Because what are you going to do if you have something in the first column? How would you find, if you have pH, how would you find POH? Yeah, the 14 thing, I would subtract from 14. So what's this what's the POH going to be in this first box? Jonathan? My first. 2.75. Good job, 2.75. All right, well, we know the pH. I need to find the H plus concentration. So let's look at all those formulas we've got on the other side. If you have the pH and you want the H plus concentration, Parker's not here, huh? Maddie, what equation could we use to find the H plus concentration here?
10 to the negative pH.
Good job. 10 to the negative, and I'll just go ahead and put it in here. 10 to the negative 11.25. Again, I want a specific answer from you here, so let's try that. Joseph, what's 10 to the negative 11.25?
5.6 times 10 to the negative 12.
All right, thank you. 5.6 times 10 to the negative 12. And that's molar. I should put molar there. Okay, now there's different ways to get the hydroxide concentration at this point. You could either do that first equation we were using at the very beginning, and if you multiply one times the other, they have to give you 10 to the negative 14. Or, I think an easier way might just be to use your POH. If you know the POH, you could use that. Sydney, what do you want to do to find the OH concentration? I like that idea. So this one here, we're going to do 10 to the negative 2.75. And Shelby, what are you getting for that answer? Good. I'm going to give maybe I guess since they gave me 4 sig figs here, I could estimate to have about 4 sig figs. So I'll give a few more digits there. Maybe 1.79, 1.778 times 10 to the negative third. All right, is this solution acidic or basic, Carter? Basic, because the pH is greater than 7 is probably the easiest way to find that. All right, let's try the next few rows on this. I'll give you a chance to just try some of these independently going across, and I'll work through it too so you can check your work as you work through there. let me know if there's something different that you got, because I could have made a mistake, or it could just be something we're working with your calculator. The other thing I want you to think about is your pH values and your pOH values. You can, I mean, it's not a perfect way to check yourself, but you can always look at those exponents on your scientific notation and see if they're close. They're not going to be exact, but they won't be off by more than one value. So if this is 12, the pH should be somewhere between 11 and 13. It's got to be within one digit of 12. Same thing with all the others. This is -4. It's not exactly 4, but it's 3.4. 8, and almost exactly 8 because this leading coefficient is almost exactly 1. Same here, -12, 11.25. So if you're really off, you'll know because there'll be a big difference between the p-value and the scientific notation on the exponent. Is anybody having any trouble? Okay. The other thing I wanted to talk about, so far, everything except on the bell ringer. The bell ringer was about an actual strong acid. That's what we're going to get into now. But since we started the notes, it's all just been about H3O plus or OH minus. We haven't had an actual acid or base in the question. So that's what's coming up in these next couple of questions that we're going to look at together. And we've got 2 on the sheet, and then there's 1 or 2 more on the PowerPoint that I want us to do together as well. About when you mix multiple acids together. So when you're calculating the pH with strong acids, it's really easy. Go back one, there we go. The H3O plus concentration is the strong acid concentration because the acid loses those strong acids, all except H2SO4, which has a little trick to it. But all the strong acids except for H2SO4, they've got 1 hydrogen that can be transferred, and it's transferred 100% of the time. So the H3O plus concentration is the strong acid concentration. Then you just use that in the pH equation. We're also going to look at a couple of strong bases. If you look at the lower sample exercises, and we're going to do those together. But with bases, you have to think a little bit harder about them. As long as it's a group 1 strong base where it just has the hydroxide on it one time, like NaOH or LiOH, there's just 1 hydroxide, then you can use the pOH equation to find the pOH. Focus on your base, pOH first, and then subtract from 14 to get the pH. With those group 2 strong bases, they have the 2-for-1 deal. They have 2 hydroxides for every 1 molar of the whole base. So we actually have to double the hydroxide concentration. Well, we double the concentration given to us of the strong base because you get 2 hydroxides for every 1 calcium hydroxide. And because of that, it takes 1 extra step as far as finding the pH. And we'll do that for the very, very last sample exercise you have on your handout in just a second. Folks, first let's look at the strong acids. Again, this is just like the bell ringer. It might even be the same acid. I can't remember. It's similar acid. So what is the pH of a 0.040 molar solution of HClO4? Well, if the HClO4 concentration is 0.040, then the H3O plus concentration is going to be 0.040 molar. Because all of that HClO4 gave its protons to the water molecules, and all the water molecules, well, not all of them, but enough of them, gained a proton so that now the concentration is 0.040 molar. Then we're ready for our pH equation. pH is the negative log of the H3O plus. I don't know why I did the parentheses here. So pH is negative log of 0.040 and it's about 1.4. All right, so obviously this solution is acidic because it's a strong acid dissolved in solution. If you put any strong acid in the solution, even just a small amount, you're going to get an acidic pH. So that one was very straightforward for strong acids. If it's a strong base, there's at least one more step, maybe two more steps, depending on what the strong base is. All right, so this says, what is the pH of a 0.028 molar solution of sodium hydroxide? And then we'll do part B in just a second. So when you're trying to find the pH of a strong base, you got to focus on the hydroxide part first. Well, if the concentration of NaOH is 0.028 molar, then the concentration of hydroxide is the same thing. And the reason for that is because when the sodium hydroxide dissolves in solution, it starts off as a solid. When it dissolves, you get a sodium, which doesn't really affect the pH, but then you get one hydroxide for every one sodium hydroxide. So those numbers are going to be equal. So let's first find the pOH as the negative log of the hydroxide concentration. Let's get Pavitra. Did you get the pOH value yet? Yeah, good. About 1.6. Since I'm going to use this in another step, I'm going to keep one safety digit since I'm not totally done yet. I will round my final answer to 2 sig figs, but I'm going to call it 1.55 for now. Keep a digit extra or two. Then I'm going to subtract from 14 to turn that pOH into a pH. And then I'll round. Whoops. And remember, in this subtraction part, don't let the subtraction limit your sig figs. So if you ever had something with like 5 sig figs, and you said, oh, I subtracted from 14, so I have to round to the ones place. The 14 is an exact number there, so don't let that affect your sig figs. I'm getting about 12.45. So I'll start with 12.5, and I guess on this one, I could take it to 2 sig figs because of that. So you could say 12.5 or you could say 13 for your pH there. I hate rounding it to that, but that's the sig figs rules to round it that way. No, sorry. No, 12.45 rounds to 12. I did a mistake. I'm in scientific notation on my calculator. It's hard to see those. Got 12. All right, so that was a group 1 strong base, so it was pretty easy. Just subtract from 14 to get a pH. On the next one, I got to think about it just a little bit harder. It's not going to be bad. Before I move on, are there any questions about finding the pH of a strong base solution? Of course, it's going to be a basic pH because I dissolved base in the solution. All right, so for a group 2 base, calcium hydroxide here, when the calcium hydroxide dissolves, it's a strong base, so it dissolves completely. You get 2 hydroxides for every 1 mole of calcium hydroxide. So if I started off with 0.0011 molar of this, well, I would get 0.0011 molar of calcium, but I don't care too much about the calcium for this. I get double the number of moles of hydroxide, and it's the hydroxide that affects the pH. So this is the number that I'm going to use when I find the pOH. pOH is going to be negative log of 0.0022. So let's get that first. And Vivi, did you get a pOH value yet? Me too, yeah. We'll go ahead and call it 2.66 here. All right, now, Alice, what do I need to do to get that turned into a pH? Yeah, so the pH is going to be 14 minus 2.66. And I guess I'll go with 2 sig figs again, so I'm going to call it 11. Kira, is this solution acidic or basic? Yeah, a great way to think about it. I dissolved a base in the solution, so it's got to be basic. And then the other way to think about it is the pH. It's greater than 7 on the pH scale. All right, so that is the majority of what I wanted to go over today, but there's a couple questions on the homework that ask you, what if you had a solution of acid and then you added more acid to it? How would you find the final pH? And it's not hard. It just gets back into using the molarity equation. You need to know your number of moles and find the molarity. So there's two ways that you could have an acidic solution and then change its pH. You could either add more acid, or you could dilute it and you could add more water to it. So this first one's about diluting an acid. So it says, what's the pH when you dilute 50 milliliters of 0.4 molar HBr, and then you just add 100 more milliliters of water to dilute it? What do you think the pH? So you've got this acidic solution, 50 milliliters of 0.4 molar HBr. If you diluted it, do you think the pH would go up or would the pH go down? There's some ups and downs. Let's find out. Let's find out what's going to happen here both. All right, so it's not part of this question, but let's find out what is the pH of the original solution then. If it's 0.4 molar, we'll do negative log of 0.4. I hit the wrong button, I guess. What's my initial pH on this one? Will Broadfoot? Yeah. Yeah, it's weird that it's like that. I think it's a coincidence there, but it's about 0.3979, so about 0.40, yeah. That will not happen most of the time, so happens to be the same number. That's kind of cool. So it's 0.4 right now. Okay, let's dilute it. Let's take that same number of moles of HBr. All right, well, remember to find the moles. I'm going to multiply the molarity times the liters. So here's my moles of HBr that I have in the first place. 0.40 molar times 0.050 liters, because that's the 50 milliliters. I think that's 50. You have to use liters. And right now I'm just finding how many moles I originally had. And I think 50 milliliters is 0.050, but I'm not 100% working today, so no problem. Let me know if anything looks weird. 0.020 moles of HBr. That's how much HBr I had. I added water to it, but that's still the number of moles of HBr that I had. When I diluted it, now I've got a new molarity. The new molarity is 0.020 moles of HBr dissolved in the total of 150 milliliters, which is 0.150 liters. So now it's 0.133 molar. Well, the concentration went down. Let's find out what happened to the pH. So now to find the pH, again, this is a strong acid, so I can just use its concentration as the concentration of H3O+. Go to the board. pH is negative log 0.133 molar. All right, find my new pH now. Ainsley, what did you get for the pH at this point? 0.876, and I'll go with 2 sig figs there, so I'll call it maybe 0.88. The pH was 0.4. I added water. Did the pH go up or go down? It went up just a little. It went up a little bit, yeah. Well, compared to 0.4, actually almost doubled there, but yeah, it went up. That's because it became less acidic. I added water to it, so the solution was less acidic as I added more and more neutral water to it. So the pH would go up closer to the neutral pH of 7, which is, if you kept adding water forever and ever, it would approach 7. I guess it would never get all the way to 7 in theory, but that's the idea there. As you add water, it gets closer to 7. So that's for diluting. The other type of question we're going to see from time to time is when you start with some acid, and then you add more acid to it. And this, will the pH go up or go down? It kind of depends on, are you adding a more concentrated acid or a less concentrated acid? So this one could go either way depending on what you're adding. But this time we're starting off with the same 50 milliliters of 0.4 molar HBr, and then we're going to add even more acid to the beaker there, but it's of a different concentration. So what we want to do is find our number of moles from both of those. We'll add those moles together, and then we'll divide by the total volume. So first we want to know how many total moles of H plus are in that beaker, and then we'll divide it by the volume of 80 milliliters to get the molarity. And then we'll do the pH equation from there. We'll take all the moles of acid, add them together, divide by the total volume to get molarity. And then we'll use pH. So the moles of HBr, it's the same numbers as before actually, so it's going to be molarity times volume, 0.4 molar times 0.050 liters. And I've already forgotten what that was. Was it 0.02? Thank you. Got that many moles of the HBr. All right, let's do a similar thing. Let's do moles of HCl, because this time we're also dealing with the HCl. So that's going to be 0.2 molar times 0.030 liters. It's 0.006. Yeah.
Would that be 0.02? For
The molarity of HCl, I think, is 0.2.
Oh, right.
Okay,
Sorry.
no problem.
I'm confused.
There's a lot of 0.02s and 0.2s up here, huh? So I think I got 0.006 moles for the HCl. Both of these are strong acids, so if I've got that many moles of each acid, I've got that many moles of H plus when I put those numbers together. So I'm going to total up my acid moles of 0.02 and 0.006. I'll do this on the board now. I'm going to add those together for my total number of moles of H plus. I don't care about the Br minus, I don't care about the Cl, they're just spectators now. They don't affect the pH or anything. The total moles of H3O plus is 0.026. I can get a molarity, because pH is all about molarity. I can get a molarity by dividing moles over liters. What's my total volume now? What volume is in that beaker up there?
80 milliliters.
Yeah, I get 80 milliliters. I've got to use liters for this stuff. So when you have multiple acids in there, you'll just add them up. I think that's 0.325. I've got 0.325 molar. Then I'll do it like it right here, down here in this little part. I'll find the pH. pH is just the negative log of the concentration, 0.325. All right. Essie, what are you getting for the pH here? I'll go with 2 since all those molarities and liters, milliliters. Yeah, thanks. 0.49. That's my pH. So with multiple acids, I just added up the moles and divided it by the total volume. If I'd had a strong acid and a strong base, instead of adding those two numbers, I would have subtracted them and figured out which one won, the acid or the base. Focus on the H plus or the OH minus, because they would, part of them would have neutralized one another for strong acids and strong bases. All right, that was a lot. Does anybody have any